Welcome to Quantum Computing Essentials Part 1, Lecture 1. So we have another lecture 0, where we have introduced the motivation of the subject, scope and potentials that merge the technology and science related with the quantum, and the focus on the quantum algorithm design. So here in the Lecture 1, we'll be introducing several the subjects which are the core parts that develop this subject, quantum computation theory. So although there are many approaches by other authors and lecture series where you can see formal approach from the physics, but we will be trying to understand this subject as engineers and technologists. So we will be starting or formalizing this subjects with the theory of linear algebra as prerequisite, and some particular facts from the probability theory. Then some parts will be covering, and some introduction I'll be giving today on quantum mechanics. Some parts from the quantum computations. And information theory. So these are the minimum requirements or the essential subjects which will help us to understand the technology, which we will call the quantum computation theory, or sometimes we'll come across the term QST, that is quantum science and technology. So we will try to understand this subject starting from the prerequisite as a linear algebra. For good readings on the linear algebra, so the readers or the audience can see some books. So for example, the introduction to linear algebra by Professor Gilverstrand, which is very standard, and you can get all the lecture series on the web. Gilverstrand. So one can see matrix computation. The book is written by G.H. Golub. And then matrix analysis by Roger R.A. Horn and C.R. Johnson. So there is another good reading that is known as matrix analysis and applied linear algebra by Carl D. Meyer. So we'll be mostly following the literature covered by these books. For probability theory, there are very fundamental books. The first one is probability random variable and stochastic processes. stochastic processes by A. Papulis. So the book, there is another book is Probability and Statistics. Probability and Statistics by J. L. DeVore. Then Introduction to Probability, Introduction to Probability and Statistics, Introduction to Probability and Statistics for Engineers and Scientists by A. Ross. Okay. So for quantum mechanics, there are many books, but one can start with Introduction to Quantum Mechanics by David Griffith. There is a very classic book known as the Feynman Lectures on Physics, and there are multiple volumes. One can see all the volumes or directly see volume 3 or the quantum mechanics part. There is another good book known as Basic Quantum Mechanics by K. Tambakis. There are other very standard books like Sakurai. So one can start from this basic literature, then go for other books as well. For the quantum computation part, so one very standard book is literature one can see as Quantum. It's a good reading, Quantum Computation and Quantum Information. Quantum Information by M.A. Nelson and Professor Isaac Chuang, I.L. Chuang. So there are other books. So another good reading is Quantum Computer Science. Quantum Computer Science by N. David Marvin. N. David Marvin. So one can obviously go for this literature, so which will help the viewers, the audience, to understand the subject in a much detailed manner. So so let us first start with some summary from the quantum mechanics part. So which is not the main motto of this lecture series, but is required at many points of time. So so quantum, even if we deal with physics, so we have many fundamental quantities, and so for the matter, and to understand its dynamics or the evolution. So some of this, the quantities are the energy and momentum, and there are other uh, quantities also, but they are treated as one of the fundamental quantities in physics. So by quantum theory, uh, uh, or we can say by modern quantum theory, so we consider both the particle and wave nature, particle plus wave nature of matter, which is described by Broglie and later used by Schrödinger and many other scientists. So the matter can be described by wave function chi as a function of space and time, and you can represent with an equation like a into e to the power ikx minus omega t. So we can put the I outside, kx minus omega t. And here k is the wave number, x is the position, omega angular frequency, and t is the time. And so we'll try to understand in a very vague manner or a very simple manner that how the classical quantities, fundamental quantities like energy and the momentum, they are related with the quantum. So that relationship we'll try to see here. That will help us to understand or connect this to subject. Then we will try to connect another part which is very important in quantum computation and quantum mechanics, that in some lecture we'll try to understand in very much detail that how a physical quantity can work as an operator. Okay. So these two phenomena are very much important. So this A is the amplitude. For simplicity, say A equals to 1. Okay. And if we take, so we have two quantities, right? So we have the quantity chi as wave function, and we have at least two independent variables, x and t. They may be of one dimension or multiple, or in the higher dimension or the multiple dimensions. So at least if we take the partial derivative of this function dji with respect to dx to understand how this wave propagate as a function of position. So and if we take the derivative, this part taking a equals to 0, so what we'll get is del x of e to the power ix I kx, and the other part derivative will be 0 for this part as there is no x. So what will come across is I k will come outside, and it will be e to the power I kx, right? So what we are trying to do is that if you bring some I this side and multiply with some Planck constant h bar, where h bar is actually Planck constant by 2 pi into del x. So of chi, your wave function. So what will happen? This I and this I are complementary. So you have k, h bar k, right? Into e to the power ikx. So this is the part, right? So if you take your f function independent of this time part, so what will come? So if it is only chi of x, then it is your e to the power ikx, right? If you take your space and time are independent, then this quantity will come as hk and chi again, right? So what is happening is that, what is this part? This is very important term. Okay, so the thing is, so we know from classical mechanics that P equals to your mv. M is the mass of a particle and V is the associated velocity. Okay, so this quantity will become the momentum. Okay, by using the quantum theory or the quantum description of the matter as h bar chi. Okay, sorry, h bar k, and so k is the wave number, and you can write it as h bar 2 pi by lambda. Okay, so this is very straightforward thing. And this P has another description. So this part is the momentum part, and this is your wave function. And if you see the equality, so this wave function is this one, right? So this has a operator notion. So del x is what? Derivative. So this derivative, that is the operator. So there is an operator notion of your momentum. If it is your equivalent P, then it is some P hat. That means the momentum can work as an operator if we use this P prime or the P hat as h bar by I del x. So h bar I del x. This is a very important equation, that how a physical quantity can work as an operator, as a mathematical function. Okay, similarly, so that means this equation will become equation of p hat chi equals to p hat p xi. So what it means is that, so what is an operator? Operator is a mathematical function. If it works on this wave function, if it works or if it acts on this wave function, it will return the quantity which is related with the operator into this quantity will be returned. So this is h bar by I del x. If you use this mathematical function and it will act on chi, it will give you return the quantity momentum and your chi. So similarly, if you do derivative of with respect to time, del t of chi. So it's a homework. Try this and try to answer this quantity. What is this quantity? Okay, so you will come across that it is the energy quantity. Okay, so that means if del x with respect to the del x of a wave function will return the momentum, del t of the wave function will return the energy. So this is related as an operator related with the P, and this is related with the energy. And this entire thing is very well known theorem known as Noether's theorem. Noether's theorem in physics. So So our basic objective is that we will see that this wave function, though it has a physical notion and definition, but in this subject we'll see that it's basically a vector, or this you can represent as a description of state, a description by state, and many physical quantities like energy, momentum. So those you can represent as operator. Okay, and they should follow certain properties. This operator and this states should follow. So a typical operator you can call as some you can call some px, that because it will act on your wave function, right? So p of x, okay, or p of chi. If chi is your wave function, p of chi is your operator. Okay, and this is the state. So state we will typically see as vector. Okay, and the operators we will see these things as matrices. So what is happening that is that if you have some physical quantities with related operator nature, and if certain operators acts on some quantum state, and it will return a physical quantity and that quantum state. So what is happening is that, so you can assume, you can consider this part E hat as a matrix of some certain dimension into a vector. Okay, say it is some n cross n matrix, and it is some vector, say n cross 1, and it will return another vector, another quantity which will have n cross 1. So this relation will see, establish as an equation in detail known as Schrödinger equation, which will connect several wave functions, or which will connect the several positions or the distribution of the wave function, so that how a particular wave function evolves over time and space. So suppose we have a wave function in some particular time and space as x comma t, and it has another description at some other time and space at chi1 as chi1 of x and t. And how those two quantities are related is that they can with this with some matrix, unitary matrix u, and the evolution may be 2 to 1. Okay, and this can be a typical functions which will be related to the kinetic and potential energy of the particular system. And also we'll be seeing this part as the evolution, unitary evolution of a particular vector. Okay, and that will return another vector. So we'll look into this subject in detail using the linear algebra. So at least we need to understand the minimum postulates, the fundamental postulates in quantum mechanics, that that your wave function chi of x. Okay, so what is chi of x? Is some wave function, is a function of space. You can take a function of space and time as well, which is a complex quantity which belongs to C. So C means the set of complex numbers, and this P of x. This is the first wave function is a complex quantity. Then your P of x dx equals to your chi x square. So the probability of a particular particular variable x into dx. So the chi of x is what is the independent variable x, the position, and the distribution is chi. That should belongs to a complex number C. Probability of x into dx will be chi square into dx. Okay. Third is the superposition theorem is that chi of x you can represent as your alpha chi 1 x plus beta chi 2x, which are other two wave functions. So any wave function can be superpositions of many other wave functions, where alpha and beta are the complex quantity, and and alpha squared plus beta squared. So they should be equals to 1. Okay. So we'll see some other details at some other point of time. So so in quantum computation part, because this wave function, the nature you don't know, so you want to represent as vector. So typically in a computer we have logics of 0 and 1. Okay. So any number you can break as at some sort of string of zeros and ones. So a wave function chi of x you can represent as kate chi. So what is kate chi? Is that kate chi is a function, is a vector of n cross 1. It's basically a column vector. Okay. And bra some other chi. Um, if it is like this, it is a row vector 1 cross n. It's a row vector. Okay. So column vectors means you have a vector like this. There are some numbers. Okay. And a row vector means this kind of settings. Okay. So so any quantum state you can represent as gate psi. So if you have only two bases in a binary digital computer, you have two bases 0 and 1. So it's a superposition. So if you use the superposition theorem, so you can represent as gate 0 plus beta gate 1, where alpha square plus beta square equals to 1. This should be validated. And this gate 0 is other two vectors. So what are they? They are, this is your alpha gate naught plus beta gate 1, where gate naught is 1 0 and gate 1 is 0 1 vector. Okay. So you can represent it as alpha 1 0 plus beta 0 1. Okay. So so obviously by 1 0 and 0 1 you are creating the superposition. Okay. And you are representing your quantum state. Okay, which is known as quantum bits or qubits. Quantum bits or qubit. So this bit, because you have 0 and 1, if you are using multiple bases, say for example you have in a computer settings, it can have three different bases, orthogonal bases. You can take as gate 1, gate 2 and gate 3, and you can create your quantum state as alpha gate 1 plus beta gate 2 plus gamma gate 3, and you can increase for higher number of bases then we will call it as Qt. So I am not giving you the whole details how this can be prepared. All those things will come later on. I'm just giving you certain definitions here. So, so basically, the wave functions we were talking. So those things you can represent as vectors, column vectors or row vectors, and there are physical quantities that we can represent as operators. So there is another word which is slightly different from the operators, also known as observables. Observables. So they both are matrices. So in order to understand the quantum computation very well, we have to understand vectors and matrices and their properties. So, in this follow-up lectures, we will try to cover some fundamental parts from the vectors and matrices and this kind of operators. So this kind of the mathematical notations, which informal name known as Dirac notation. Okay. So we'll try to understand this vectors and matrices and their several properties, and use the direct notation to understand the Schrödinger quantum mechanics and the quantum computation uh, in a broad sense.